some sort of like scented thing around the beer.
As she should, just to take care of
It
it.
all a week.
Yeah.
It was just the scent power has to fight against like the
Months
dirt
of
and
stink.
like grime smell. I don't get into my truck; it's disgustingly stinky.
I don't know about that. You're not selling it.
It's just from like working outside.
No, I get that.
Let's just say we're lucky we're wearing masks.
Yeah. Yeah.
It'd be like a plague doctor and have like potpourri.
Incense in here,
Yeah.
yeah. Mine's just like full
That'll
of
stop
spices.
viruses. That's fine. Get some like frankincense in there.
Hello.
Yeah, I think I'm just gonna, normally I have like a, so I have Tyler and Connor is also gonna be joining us by Zoom. We'll see how it works. I'm probably just gonna have to do one of these. There's not gonna be much board work today anyway. We'll be on Mathematica and I'm gonna be doing, I got Astrovice together today. You'll be proud of me.
No, I remember. I appreciate, I mean, I haven't, yeah, but the homework is less brutal than fluids by like several orders of magnitude. So
We have different philosophies on homework, Pogo and I.
fluids has a 15-point rating ODE on first homework.
Yeah.
So,
He also likes to front load his, he likes to intimidate you.
Yeah,
I think with the first homework is always the hardest one, it seems. I don't know if that's true with fluids, but it is certainly true with mathematics.
it was true with me.
Yeah.
That first test was legal, and the second one was like, this is all just one line of code. So
Right, which is why you can't use it for the rest of the test.
Right.
Which we,
Then it also just be one line of code.
you just gotta know, exactly the right syntax. That's the problem.
That's,
As with all coding.
I think that takes my original fear all the way to global, so. It's gonna be rough. You notice he just forwarded me in the first video though? He's like, math results, these are terrible. This can't be right. And I'm like, ouch, I'm not even ready. I can defend myself. This is just a video. He's just in his office making fun of me. They weren't bad results, to be fair. It was dragging a box and counting dots.
Oh, good time. Since last time I taught this class.
Dr. Steinhauer, were you going to post Friday's video up on Canvas or Friday's Zoom?
Oh, yes. Did I not do that?
Yeah, I was
I
only
will,
seeing one day.
This Friday's lecture to Canvas, yeah. I guess I haven't.
All right.
You can't see everybody, but everybody can see you. You can wave. You're up on the board.
Hello, friends.
I like that you think of it. Other people say, what about that? I'm like, we make these machines, but the problem is we're not really sure what we're looking for. So that's really sure from the machine.
Yeah, it's not the part of this class, which is the other reason I kind of picked it, because it's one topic that isn't covered in this class. It's an extragalactic astrophysics topic, so I assume, who's taking extragalactic? Just, oh, and Tyler. Yeah. Do you spend I would spend a good week or two talking about dark matter if I were taking that. Okay, good.
Wait, do you have students, and do you have to have students in the physical classroom right now?
I do. Would you like me to show you?
Sure.
Yeah, this is, we're all
Hi,
here.
everybody.
Hello, friends.
And hi, Tyler.
Yes,
I
we're
didn't
back to
realize that.
someone to normalcy now, which is
Yeah,
nice.
some of my other classes decided to keep being online for a while, so I assumed that was the case for this one too.
Oh, no, we're back in person. If you can run over here in the next minute, you're welcome to join us.
It would take me about 5-10. I think I'll just do it for Wednesday.
Okay, that's fine. That's fine. Do what you gotta do. Connor was on earlier. I'm not sure he was expecting that. No. You'll hear from me if something ever does happen and we have to go virtual, you'll either hear from the president or of the college, or you'll hear from me if something happens, like, I don't know,
Okay.
class specific. But otherwise, it's an in-person class. We're here doing our thing. Okay, cool. 2, 4, 6, 8, 9, 10, 11, 12. I'm missing one other person. Who is Miles. Okay, cool. What are we gonna do? All right. So today I am going to do the Astrobytes article. Although I'm missing someone else too. Where's Dan? I missed count. 2, 4, 6, 8, 9, 10, 11, 12, 13. No. 14. Oh, maybe I'm only counting to 13. So Dan knows the other one. Anyway, Dan O is on schedule for Astrobytes this Friday. So I was going to put him on the spot and make sure he knew that he was not allowed to pull Steinhauer and just come unprepared. But I guess he's not here. Anyway, so very nice to have the other people in the classroom. This is a breath of fresh air for me, even though I can't really breathe it in all that deeply right now. Right, and Astrobytes. So my excuse for last week is that it didn't really feel like the first week of classes, because I had been making videos for my intro class, because that's all asynchronous. And last week just felt like making more videos. It didn't really seem like classes. That's not really an excuse, but I'll use it. Okay. So the Astrobytes that I am talking about had a very provocative name. Let me just share my screen with you guys. Finding fire-breathing dragons in the Milky Way. And it had nothing to do, of course, with fire-breathing dragons. And I don't think fire-breathing dragons were mentioned in the article itself, but the person who wrote this Astrobytes did a good job of giving it a provocative title and even tying it into a quote from Carl Sagan. So that was nice. But let's talk about what the topic really was about. All right, here we go. You guys seeing this on Zoom? Okay, cool. So this is an Astrobytes article that was written by Zili Shen, who is a grad student at Yale. You can read. Hey there, Dano. Welcome. I think there's some. Oh, you found the spot. Okay, cool. Okay. Who's a grad student at Yale. There's a little nice bio at the bottom if you can go and see all these people. So that's cool. The article itself was from 2019, written by Bonacca et al. I can't remember where they're from, Boston University maybe or something. Doesn't matter. So here we go. This article talks about the dark matter halo. So if you don't know, let's talk a little bit about dark matter. We know that 85% of the mass of the Milky Way is not in normal baryonic stuff. It is not in protons and neutrons. It is in something else. And we don't know what that something else is. And it's 2021. It's kind of embarrassing. But the interesting thing is, it is spread out diffusely throughout the entire galaxy, and in fact extends well beyond what we would see as the normal edge of the visible particle. So this is the dark matter field. And honestly, the dark matter is the galaxy, right? That's 85% of the stuff. The baryons, the protons and neutrons and stuff that would form stars, fell into the potential well that was created when this dark matter mass contracted at the beginning of the universe. So in some very real sense, the dark matter is the galaxy, and the thing that we can see is just the stuff that fell into the bottom of the pit it is the galaxy itself. But so that's been well established fact. We've known about this since the 60s and 50s. Now, the question is this some sort of smooth, continuous distribution of stuff? Most likely it's some elementary particle, like a neutrino-like thing, that is moving slow enough that these particles are probably bound in some way to the Milky Way, which is an interesting thing. Now it seems that, in fact, this is predicted from models of cosmology, that these dark matter particles should come in clumps. And so it shouldn't just be a smooth distribution of dark matter in the galaxy, but there should be some of these substructures, some dark clumps associated in it. So those subhalos. So that's what this group is trying to find. They're trying to find evidence of substructure within the dark matter halo itself, which is fine. So let's briefly review what the dark matter halo is and why we know it's there. This is the canonical observation that was made in the Milky Way of the galaxy to determine the mass of the galaxy. It's pretty easy. We understand Keplerian orbits. We understand classical dynamics fairly well. And you can, this is a very well established effect. The orbital velocity of something around another object is equal to the square root of g times the mass of that object that it's orbiting divided by the distance from the center of that object. So if this were, you can do this with the Earth, satellite from the Earth, or the Earth and the Sun, you just go with the mass of the Earth and the mass of the Sun, and how far you are away from the center of that object, and you get a circular orbital velocity. Now, in the case of the galaxy, this isn't the mass of the whole galaxy, assuming some spherical distribution of matter. This is the amount of the galaxy within your orbit, right? Not only can this give you the entire mass of the galaxy, it can give you the mass of the galaxy as a function of radius from the center of the galaxy. So that's a pretty simple thing to do. We can just measure the mass directly by measuring how fast things are orbiting the center. When we do that, we find almost all spiral galaxies have this flat rotation, which is that once you get outside the very center, the orbital speed does not vary much at all as you go out, which is interesting. It implies that the total amount of mass increases linearly as you go out from the center. It implies a very specific mass distribution of the galaxy, which falls off as sort of like 1 over r squared. But you still have an r there as 1 over r cubed, and you're increasing the mass of it. And that this mass goes up exactly the same rate as that mass to keep this constant. Now, if you add up all of these stuff that you can see, the stars and the gas and the dust, you get a curve that will look like this. Maybe plus this gas thing. You cannot explain how fast these stars, especially the outer part of the galaxy, are moving with only the matter you can see. Therefore, there must be something there that we can't see, therefore dark. Right? We have other reasons to think now that dark matter exists. This isn't the only reason, but it's still bothersome that we don't know what 85% of the galaxy is. And it's even worse than that. We don't know what 95% of the universe is. We think that ordinary matter is only about 5% of the total mass of the universe. So this is a problem. Anyway, we don't know what it is. We're looking for it. We're trying to find the particles that it would be. No luck. In the meantime, we can characterize it and what it does and how it works. So this paper looked at tidal streams of the galaxy. So these are probably mostly satellite galaxies that have been ripped apart tightly as they encounter basically as the Milky Way is absorbing them and eating them and cannibalizing them. Sort of like a comet, you know how comets work, same sort of thing. If you have periodic comets, they leave a debris trail. It follows so much like, and if you're having to pass through the debris trail, we get a meteor. This is what meteor showers are. Passing the debris trail of the comet. Same sort of thing. All of these particles should orbit roughly the same direction and the same total plan in the galaxy. And so this provides an opportunity to see, this particle is traveling the same path as that particle as we move through, but at different times. And so if it gets disrupted, you can make assumptions about what's going on. So there's roughly, if you do the Wikipedia article for tidal streams of the galaxy, there's 23 things listed. I don't think all of them are confirmed. And these things are really hard to observe, right? Because we're here looking at this tidal stream, it doesn't show up that much. In fact, satellites like Gaia are helping us identify these things because they'll all move in the same direction and they'll all have about the same distance from us, at least a certain part of the tidal stream. So finding distances to things, but more importantly, we haven't talked this word yet, proper motions. Proper motion is the velocity of a star through the sky, how fast it seems to be moving on the sky from us. And all of these things should be moving in a stream in the same direction. And so they'll stand out on a diagram of, how fast, in a vector diagram, a velocity diagram. And they're moving very differently from most of the stars in the galaxy if they're moving around in a circle. So they stand out on these proper motion studies. Anyway, that's neither here nor there. So this is that proper motion diagram. I think these are velocities in two directions, phi1 and phi2. In this particular thing. And anyway, you see some interesting content, which is that there does seem to be some disruptive events, right? There's a region where there should be stars there, and there's aren't any stars. There should be stars there, this was a bigger gap, but there's far fewer stars than you would expect from the points here. So, and you can see features where
Oh shit, Bitcoin.
stars that have been disrupted from that stream and sent over. This can happen when you get a close encounter with another massive gravitational object. So if a globular cluster passes close to the stream, for instance, globular clusters can have hundreds of thousands and millions of stars in them, right? That can tidally, gravitationally disrupt how these stars move through the galaxy and throw them off of their normal trajectory. And so they can use this as clues about encounters with massive objects, even if they're unseen in the halo dimension. And that was what they were trying to do. So this is the only diagram that the asteroids article showed, but I went to the article and got another couple of diagrams. This is showing simulations, right? They did a numerical simulation of gravitationally bound system. They had the tidal stream go by. They moved something massive past it. They varied how big that thing was, how massive it was, and how close it got to the tidal stream to see how much it disrupted the tidal stream itself. And these are some of the profiles that they got out on how that interaction changed the morphology of the stream itself after the event. Just some ideas, right? You can have any really thing at all. It looks like we had something like this go on, right? We had some cusp that was moving off in this direction. So you kind of see which of these events are ruled out and which ones are supported by the actual data itself. That's cool. I don't know if you noticed the two of these. This is the actual data, and this is a simulation, one of many that they did, the best one that they found. And so this particular simulation had an encounter with a massive object that had 5 million solar masses about 500 million years ago. I'm guessing, I don't know if you remember that, probably sizes, like roughly 10 parsecs, moving at about 250 kilometers per second, which seems fast, but that's not atypical. The sun's velocity around the center of the galaxy is 220 kilometers per second. So that's typical of things moving around in a circular orbit around the center of the galaxy. Okay, so then they went back and thought about all of the known big massive things in the galaxy. Things like globular clusters, which have hundreds of thousands, millions of solar masses. Things like very faint dwarf galaxies that are in the process of being absorbed in the Milky Way, but are still orbiting in some other weird things like, these are both kinds of galaxies, things like the disk of our galaxy. And they found, like they know how each of these are moving in the galaxy, they move around the clock, and this is how close each of those things got to this tidal stream in looking back 20 million years, 15 million years ago. None of them, aside from the disk, obviously the thing does pass through the disk, close to the orbit, none of them got anywhere. This is a long scale. This is how close it has to get to explain this thing. This is in parsecs. This is 100 parsecs, 1,000 parsecs. None of them got within 1,000. And it has to be well less than 100 parsecs to explain this. So their claim is there's nothing known that could have caused this disruption. It had to be something we can't see. So it must probably, their guess is, it was one of these ultra compact substructure in the dark matter halo. This is a cool thought in the picture in the paper as well. This is mass of things. This is size of things. Right? These are all the globular clusters, up to about 1 million solar masses or so, contained within a size of 10 parsecs or so. These are all of the outer disk molecular clouds. Some of them very, very massive, but very different. Like these things are very low density compared to globular clusters, so they are much larger in size. This is the box that they think contains the parameter space of the object that did the damage to the tidal stream. It fits globular clusters, but there doesn't seem to be any that we know of that actually came to that. These are dwarf galaxies. Obviously, it fits some of these dwarf galaxies, but again, none of these dots actually came close to it in time frame. This horizontal line is the prediction from current cosmological models of how big these dark matter subhalos should be. Right? This is sort of the size range of what they should be. And you can see there isn't much overlap, but there is some overlap. So it's possible that something in the 3 sigma, 2 sigma range did overlap with this and caused this thing. So I wouldn't call this definitive proof, but it is interesting evidence that sometime in the recent past, 500 million years ago, this tidal stream got jostled by a close encounter with a subhalo dark matter. Right, that's way more than 5 minutes. But questions, comments, discussion. That's a good question. I didn't read the article. They did many of these simulations. So yes, they have data, right? And then they, in a computer model, did many runs where they had this tidal stream that was in some sort of orbit and moved something by it fairly closely. And they watched how that affected the tidal stream 500 million years later, or however long it was later. And they did that until they found one that got the best with what their observations were. So this is kind of a hunt and peck. And that's not to say that this is a single run with a single mass and a single impact parameter, but this is how big the thing is, and this is how close it got, or something like that. Itself and a single time, right? There was a huge parameter space that they said was allowed by the data that gave you something that looked like this. This is just a single line. That's sort of the best fit. You can see how it can reproduce this gap, it can reproduce that gap, and it can reproduce the sort of curve of the stars that got split cut up in the middle. So I'm not trying to do that.
Dr. Steinhauer.
This one? Oh, no, this one. Oh, one of the what? Right. Right, and it would be happening to all of the parts of the screen, right? I think that the thing is, it can't be the disk because all of the parts of the screen stream through the same part of the disk as it goes through, and it would affect all of them. In the same way. This had to be an event. I think it was a singular event that caused this weird distortion. Right. That's right. And so if it affects the stream, it will affect it. It will affect the stream in the same way. All of it. And I think it's not. I think it's much bigger also than kinds of events that happen. Meaning in terms of stock. Certainly bigger than person. Yeah, again, the substructure of the halo of the galaxy, of the dark matter, I don't know that we know the answer to that question definitively. I'm guessing that it doesn't have certainly a disk that's as thin as the stars are settled down into. But I don't know that for sure. I don't think anybody else does either. This equation that we use assumes actually that it's a perfectly spherical distribution. There is no disk at all. And I think that that's a pretty good approximation we think of what's going on. There could be some diskiness to it, but it's certainly not this flat. I think this is our kind of our picture, right? There's a diffuse halo that sort of surrounds the whole thing in some spherical way. Cool. All right, thanks for the discussion. Dan O, you're on for this Friday. You want to send me something by Wednesday? Okay, cool. All right, where were we? We were, oh man, this is tiny. Let me make this way bigger. Ah, that's better. Let's make it even bigger. So you should pull out where we were last time. We were talking about the Planck distribution. And we were doing some mathematical stuff. And we had gotten to the point where we had determined that the place where this function peaks for different temperatures is inversely proportional to the temperature. As we decrease temperature from 10,000 to 5,000 to 1,000, the peak wavelength went from 289 to 579 to 2897. And it seems that it's inversely proportional. So we should have some equation like this. Lambda max equals some number, some constant divided by 2, proportional to 1/2. So our next job is to figure out what the proportionality constant is. And we really already have it, right? Because this number has to be lambda max times t. And we have a bunch of lambda max. We have 3 lambda maxes and we have 2 t's. We multiply those 2 numbers together. In each case, that'll give us what this number is. And that will tell us what lambda max is for every other. We don't have to worry about solving differential equations or setting derivatives equal to 0. So lambda max proportional 1/t, we've gotten to that. Zoomers, can you read that at all on the board?
I can. I think most of the trouble is microphone pickup, but the board looks
Oh,
fine.
I see. Would it be helpful if I put in a earbud?
Possibly.
Probably, yeah.
All right, let me try that. Okay, is it going through the earbud now? Not really.
Hard to tell. Maybe if you step away from the desk.
Okay,
and
we'll,
face
we'll, we'll
away.
figure it out. It would be better or won't. Okay.
I mean, yeah,
So sorry.
it's workable as it has.
Right. Actually, I'm still hearing you through here, so it probably is not. How about now? There you go. Now it's switched.
That's pretty good.
Let's
Yeah, it sounds
let's just
clear.
let's just do this. We can. This is in nanometers, so I'm gonna. Here we go. This is. So I'm going to show you, I'm going to type some stuff in. You guys can follow along. I don't think I did this last time. And I'll tell you what it is I'm doing and why I'm doing it. So this is, I've got a functions, I've got a solution sol, which is this, which gives me the wavelength in nanometers of the peak, right? And I know this was at 1,000 kelvins. If I take, this is to get the last sol identifies this, the x/dot identifies the number associated with x in this. So this is all a way to just get this number out. And I want to make that, I've stripped all of the units out of this stuff. So I want to move it back, right? I want to tell that this is in nanometers, and then I want to multiply that by 1,000 kelvins, which is temperature times lambda max, which is what I'm doing right there. This is just a way to do that in Mathematica, keeping the units. Let me just, okay, cool. So I get 0.002897777 meters kelvins. And that's pretty much all I need to do. That's the number. So if I write this down, I get 0.0029, let's say, meters kelvins equals lambda max times T. This formula has a name. Do I know what this formula's name is? It's Wien's law. That's right. Wien with a W, Wien's law. So this is often written lambda max equals 2.9 times 10 to the negative 3 meters kelvins per temperature. It's the same formula. So you don't have to do this anymore. If you know what the temperature is, you can tell what, for this black body, for this perfect radiator, what its peak wavelength will be. Okay, the sun has a temperature of about 5777, at least that's according to the T-sun, 5777 K. If you plug that in, you get lambda max of 502 nanometers. which interestingly is in the green part of the spectrum. Why doesn't the sun look green? What's that? No, it's a good guess though. So you think that astronauts in space saw see the sun as green? It's a good guess though. Our atmosphere does change the sun color a little bit, makes it a little redder. No, it's because it's a distribution, right? So the spectrum looks like this, right? Green may be here, but there's lots of yellow and lots of orange and lots of red and lots of blue also. And our eyes synthesize all of those colors together as being kind of yellowy. So it's because if it were a spike and you were only seeing green, it would look green. But that's not what it is. And our eyes synthesize that whole thing as kind of yellowish white. Okay, cool. For the homework, you will be deriving, that's not good. Somebody used duct tape on this board. Probably the same person who did that. You're going to be deriving the Planck's law equivalent for frequency space. So B nu, so we wrote down B lambda, which is Planck's function as a function of lambda. This is B nu, Planck's function as a function of frequency, and it's 2 pi nu cubed over c squared, 1 over e to the h nu over kt minus 1. So, warning, it's going to be tempting because you know that, right, c equals nu times lambda, right? Wave speed is equal to wavelength times frequency. It's going to be tempting to say, well, that makes finding the maximum of this function really easy because all I have to do is plug in, I know what c is, I can solve this for v, but that doesn't work. It is not true that nu max is equal to c over lambda max. It's tempting to want to do this, but it doesn't work. And it doesn't work because these are fundamentally different things. This is per unit frequency, and this one is per unit wavelength. And they actually, the functions will peak at different points, which is part of the things you're going to explore in the homework this week. So you'll have to use some numerical techniques to, like we've done here, figure out what that function is. And you can probably do a similar thing that we did with the wavelength, except that this is not coded into Mathematica the same way that the wavelength function is. Oh, yeah, you're right. It's not pi. I messed this up. This is not a pi, it's an h. That's important. Thank you. You're also going to need to find the inflection points on the wavelength scale, right? So we've used, you take the first derivative and set it equal to 0, you get this point. To find the inflection points, you need to take the second derivative and set it equal to 0 and find the points that set that equal to 0. And there should be 2 of them that are close to the center. And so that'll be a fun exercise too. Okay. So you can't use find maximum in that particular case. So let's find out another way to do this. And let's get rid of units. So let me show you how to do some of this stuff. Because we're going to need Planck's constant without the units. And there's a way to have Mathematica tell you what that is without having to type it in. So check this out. Did you know Planck's constant was in here? That's not Planck acceleration. Planck constant. And it knows that it's h, right? So I can say, obviously this has units. I don't want to have units. So I could say quantity magnitude quantity Planck constant, and it will tell me the value of Planck's constant, which is in units of Planck constants 1, which is actually not that useful. But if we do unit convert, actually we need to do unit convert first. If we do unit convert quantity Planck constant and we convert it to, actually we just do this, I think it's still, oh, I'll give you some crazy thing. Actually, that's not bad. This didn't used to work. I think that SI base is now normally, last time I did this, I would have to use SI base. I don't think I have to do that now because SI base seems to be the default. So you can have SI base in here, which means SI units, give me SI units. But it looks like that's the default now anyway. So I can now say, I'm not going to call this H because it knows what H is. I'm going to call this HH equals, again, I want quantity magnitude. I don't want the unit associated with this quantity. And I think all of that will give me that. And I think that is my Planck's constant. If I do HH/n, I've got 6.626 times 10 to the negative 34. That's a lot. It may be more complicated than typing in 6.626 times 10 to the negative 34. And you're welcome to just type that in. But they're all built in here, and you can use this to do any unit, pretty much any constant you want. So let's do, and now we can copy and paste this. Let's say you want the speed of light. Speed of light. It's there. Got it. It's in there. Two is to way more precision than you're going to be. In fact, look at this, how precise this H value is. In fact, that is now the defined H. H is one of those constants that went from there's no clock in the back. If I start to go over time, just raise your hand and let me know. That went from calculated to, oh, there it is. That went from calculated to defined. And this may be the defined value now. I don't actually know. Anyway, this has infinite precision, not infinite precision, but this is as precise as you need to get. Anyway, that's neither here nor there. We can do Boltzmann's constant too. Let's call that KK. Boltzmann constant, bam, done. That didn't work. Oh, I forgot what happened. Yeah, I thought I just put it in. Oh, there we go. It worked. Perfect. Great. Now let's actually do this the hard way. So I'm going to say let's actually define our B function, our B lambda function. So I'm going to say escape L escape to get a lambda. There's no escape button on this computer now. I'm a little disappointed by that. So lambda and T are my two variables. And this is going to be equal to HC squared over lambda to the 5th power times 1 over the e to the function is exp of HH times CC divided by lambda times K times T minus 1. I think I did that right. I should be able to plot this now. Plot, let's say, always a good idea to make sure that you function is doing what you think it's doing. So let's say lambda and 10,000 to give us a 10,000 K spectrum. And I can plot that, let's say, from lambda from 0 to 10 to the negative 6. Bam. That's what I expected to be. It gives me the Planck function. So we've got the Planck function here. That's good. We can take the derivative of this function now. Mathematica can do that just fine. So I can say d of b of lambda t as a function of wave. I'll take the derivative with respect to wavelength. Again, that's some crazy numbers, but it doesn't really matter. It knows what that function is. And can take the derivative of it and can plot it. So let's just plot this thing. I'm going to put this whole thing in here. From lambda from 0 to the 10 to the minus 6. Uh-oh, that didn't work. Not a valid variable. What? I didn't type that in. You typed that in. Let's try this. db. Let's try making a new function. Oh, maybe I didn't put in. Oh, I didn't put in a temperature. That was my problem. Here, let's try this. Right, it needs a temperature. They can't plot it for all temperatures. This needs to be like 10,000 or something. Boom, there we go. Nope, that didn't work either. Whoa. Ten to the minus 41. What? Question? Why are all these negative? What did you do differently than me?
You switched your temperature.
Oh, yeah, I did. Yeah, I do. There we go. That's what it should look like. Okay, so you can see it's equal to 0 at one point. Whoa, I'm about to run out of batteries. This is weird. And so that's where we can numerically set this equal to 0 or find that root, and it will tell us what that number is. So I can say find root of dB of, let's say, lambda comma 10,000, and tell it to look, give it an initial guess of, let's say, 3 times 10 to the negative 7. And it should numerically solve this equation basically and give us the answer. But it did not. I did put X here, didn't I? There we go. And this is exactly the number we got before, right? So this is just another way to get that Bean's law constant out. But the way we used before will not work for this version, and it will not work to get the second derivative. So this is a more useful set of step-by-step instructions to get the answer to this thing for the homework, and also the second derivative of this thing for the homework. No, this is in meters. I think it's 10 to the minus 9 or 10 to the minus. That's an interesting point. Yes, but it's also 10,000 Kelvin. So this is just the wavelength. You have to multiply that by 10,000 Kelvin to get this. And I think that's in meters also. You multiply that by 10,000 Kelvin, you get this number, which is meters Kelvin. Right? Yeah. Okay, cool. So you can do this with other temperatures. Again, you should get numbers here that are always, you multiply it by the temperature and you get that number out. And you can take the second derivative now and do the same thing. Take the second derivative, you should see two inflection, you see two values where this thing crosses the crosses zero. You can solve for both of those roots. Yeah. I don't mind at all. Did this one? This one, sure. Yeah, this is the Planck function, 2hc squared over lambda to the fifth times 1 over e to the hc over lambda kt minus 1. No problem. Okay, cool. We can also have some fun with integration. So let's, how much of the flux is, let's say, at wavelengths greater than the peak, right? We can solve that pretty easily now. So we can do things like and integrate B. I'm going to stop typing wavelength and just type L's. L, let's say 10,000. That's the original Planck function. And let's say I wanted to go that from lambda max. So I could either, I should probably save this as a variable, but I'm just going to type it in there. From that to infinity. Right, and this should tell me how much flux is contained in the everything to the right. All right, well, that's a lot of flux, and it's probably in some weird units like joules, which is interesting, or joules per wavelength per steradian or whatever it is. But more interestingly is what fraction of the flux occurs there. So let's take this and divide it by, oops. The same thing, except let's go, oops, I forgot my Y, except let's go from 0 to infinity, right? So this will give me the fraction that is longward of the peak. And that number is about 75%. So interestingly, although it peaks at a certain point, it's not a symmetric distribution. Most of the energy is contained to the longer wavelengths. And only about 25% of it is to shorter wavelengths. So that's interesting. Yeah, I think that's right. Although, if you were to take the visible part of the spectrum, right, it goes from like there. This is a very, very red, very blue star. It goes from like there to there. So right, even most of this flux is blueward of it because the peak is the blueward of the visible part of the spectrum. But even if this were a visible part of the spectrum, a lot of this would be in the infrared, right? It falls off pretty quickly over here. There isn't much UV light beyond a certain amount, but there's a huge tail that keeps going and going off into the infrared, and that carries a lot of energy actually out there, even past the visible part of the spectrum. But yeah, that's right. Okay, we're out of time, and I'm about to run out of batteries. I'm gonna have to bring my charger if we're gonna be doing Zoom and mathematics stuff. All right, and I think that's pretty much all you need to do the homework this week. So I'll have fun with that. And we'll meet back here on Wednesday.
Thank you, Doctor. I'll see you in class.
See you, Hunter.
Thank you.
Have a good day.
Bye, Connor. Why do we do that? This was, so this is going to tell us the fraction of the flux that is longward, right? So it's interesting to find all this flux, right? But more interestingly is what fraction is that as a total, right? So so this will, if you divide that by the integral onto the whole thing, then that'll give you the fraction. Or you can stay. I don't mind. And it's the same problem for every time they need to use. We're going to be doing the Kepler's lab. Yes, it's going to be a problem also. From now until, right, you know our lab. We use image j almost every day. It's going to be a problem. I assume image j is not available.
Section has a website that allegedly allows you to use ImageJ in the browser. I'm going to check it out tonight to see if it actually works. But
Yeah,
if it
that would
does,
be
I'll
useful.
forward it to you. Yeah, absolutely.
That would be useful.
No, so she had an issue because
Let me know too.
she didn't have the actual, she didn't have the Java update, and instead of, she didn't know how to update Java,
Oh.
and so she found this like
Let's
website,
just
but I'll
look.
send you the link, if
Let's
it
just-
works.
let's
I'm
just do
testing it
Google.
tonight. Okay. Because I don't know if I should trust it. And if it doesn't work, it's gonna suck for her, because then I'm gonna have to walk her through a Java update, but, which isn't even hard, it's just.
But I was like, this, I know that this is.
You know what, let's see if I can find it. She sent it to me in an email.
Yeah, if that works.
That would be
He
massively
used
convenient.
having to borrow a laptop.
Also, Sean, that kid whose laptop broke, and then he said he was gonna borrow one, have not heard from him.
Yeah.
He said he was
Run
gonna keep
image
me
J in
posted,
browser.
But, yeah, I don't know, we'll see.
Also,
Yeah,
different
yeah,
line
yeah, look at that. Is it doing it? Is it doing the thing?
It's thinking about it. You probably still need the Java
Let
update.
me see the.
is there a way to see if somebody joins the
Yeah, that's the
class,
website.
like after we met for our first lab? Because there's a name that I don't recognize on Canvas. That was
Oh,
not on my list of people to expect on Zoom.
I see.
So I don't know if they joined.
I don't know if I have access to when a person joined your
Okay.
lab.
No way. No way. That,
What?
Is
All right,
that-
so let me try this.
yeah, because that's the website she's using.
Let's just drag one of these guys in here.
That'd be super cool, not gonna lie.
This is looking promising so far. Although that's not working.
Let me see. Fiddle around a bit while you're-
Not sure why it's not letting me click on that import.
Oh, yeah, like those kids. Yeah.
This takes forever. to
Oh,
load,
yes,
though.
yes, that is, I know exactly what you mean.
Oh, hey. Ooh. Come on now. I want this to work so bad.
Drop file here to open.
You
Doesn't
know,
seem to be opening now. So
that's poopy.
try reloading it.
Are we letting them use the web version of it?
Well, I've learned that it just exists 2 minutes ago. So this is a worse, this is a, you know, I have a Chromebook and, or
Yeah.
I have a Java
Okay.
update that didn't
Mine
work.
opened. Mine opened.
Oh, your computer is at 1%.
It's on what?
1%.
Yeah, maybe that's why. Mine opened though,
possible.
so
Yeah, I'm about to die.
Okay.